Good morning. I think everybody knows me, but just in case, Mark Williams, I'm the president of the college. It's my pleasure to moderate our TED-style talks for this morning. We have three outstanding speakers. I will confess that I was not involved in the selection of the speakers, but I'm extremely pleased that all of these are good friends and collaborators, and I think we're in for a real treat. Our first speaker will be Heidi Rehm. She is the Chief Genomics Officer and Professor of Pathology at the Broad Institute in Harvard. She's co-director of the program in medical and population genetics, and she's PI of a number of projects that we've worked together collaboratively, including eMERGE and ClinGen. Joe McInerney is retired, but that really doesn't sum up Joe's career. For those of you that know Joe, it really is just claiming to be retired, yet here he is. He's an icon in genetics education, and he was the director of the Biological Sciences Curriculum Study. He spent 10 years as the executive director of the National Coalition for Health Professional Education in Genetics, affectionately known as NCHPEG, and also served as executive vice president of the American Society of Human Genetics. And then our last speaker, Ellen Wright Clayton, is professor of pediatrics, law, and health policy here at Vanderbilt University School of Law. She is an international leader in health law focused on the conduct of genomics research and translation to clinical care. She's a PI of Transdisciplinary Center of Excellence in Ethical, Legal, and Social Implications Research. And we also had the pleasure to work together on the eMERGE project. So with that, we are going to launch into the speakers and enjoy the session.
Thank you, Mark. And welcome, everybody. It's a real delight to be here in person for a change. It's been a couple years. So I'm delighted to talk to you today about incentivizing knowledge sharing, the story of ClinVar. So I have no disclosures, and I thought I'd just start out and think about some of the milestones in launching databases of classified variants. And I sort of start back in 1996 with the Human Gene Mutation database. This was led by David Cooper and was really focused on gathering variant and evidence out of the published literature. And the benefit was really that we could overcome some of the challenges in finding variants in the literature, which still remains a challenge today. However, some of the challenges when focusing on the primary literature is there's a lot of errors in interpretation and over-interpretation when just focusing on published literature. And there hasn't been any capture of benign variants in that database, which is one of the actual more useful things about some of the published literature. Then in 2005, the Leiden Open Variant Database software was developed by Johan Dundunnen and his group, and that was actually quite useful for a lot of the researchers working in specific disease or gene-specific areas, because for very low cost, they could launch an online database to share their curated knowledge in certain genes and disease areas. However, there's still only a limited number of disease-specific databases, and many of them haven't been maintained over the years. So a lot of us recognize the need to really engage the clinical laboratory a decade ago now, because we recognize most variants from clinical labs were not shared publicly. And in fact, many of the laboratories, my own included, were doing redundant curation work, curating the same variants, reading the same literature, extracting the evidence. Meanwhile, a lot of the cytogenetics laboratories about this time were collaborating to share data on CNVs and define standards for cytogenomic microarrays, which were starting to be produced by different vendors. They were trying to create consistency in the backbone of these arrays. And so the ISCA was launched, part led by David Ledbetter and Krista Martin, to really get this community working together, sharing knowledge, and helping help guide the design of these cytogenomic arrays. That data was being shared into dbGaP, but it was very difficult to access, particularly for the clinical communities. Meanwhile, we started piloting and pitching other solutions. Initially, a group of us began working in part with Patrick Willems, and we launched this muted database concept. And it was sort of a combined commercial/free model where users would pay to access, but the contributors could get free access. And it was working a little bit, but there was still complexity. How much data did you need to contribute to get free access? And there was concerns about sustainability. Meanwhile, I had companies coming to me pitching interesting ideas of complex ecosystems of microattribution. For every piece of knowledge you share, you'll get a little fraction of a penny for each time somebody accesses that, and we'll create this whole ecosystem of payment and distribution. And I just thought, this is going to be a disaster. No one will share data without somehow wanting to get paid for it. And all of these solutions had problems creating incentives, building trust, and importantly, demonstrating sustainability. So back in about 2011, a group of us approached NCBI about building a variant knowledge base. And in fact, NCBI had already begun planning for such a database for clinical variants as an expansion of dbSNP and to support the genetic test registry, which they wanted to be able to add specific alleles to different tests. And critically, NCBI had a reputation, and still does, of building and sustaining valuable resources for the genomics community. There wasn't this issue of commercial bias or conflicts of interest, and immediately we began working together between the clinical labs and NCBI on the concept of a variant database. Now, we also needed to obtain some funding to really establish some infrastructure in the clinical lab community. We actually, between the ISCA cytogenomics community and the clinical sequencing labs, came together, submitted a U41 genomic resource grant. Now, that first grant wasn't funded. I remember reading the reviews, and it was mostly from the research community saying, why would you ever build a rare disease variant database? All genetic testing done right now is for pharmacogenomics and complex diseases. I thought, clearly you haven't been to the clinic lately. And so, it was clearly we needed to educate about the importance of rare disease diagnosis. So we rewrote aspects of the grant, resubmitted that grant in 2012. Meanwhile, the NHGRI launched a clinically relevant variant resource, RFA, recognizing the need to better define important pathogenic variation in this field. And 2 grants were selected for funding that I've listed there. And then in 2012, NCBI launched the ClinVar prototype. And then in 2013, the full database was launched that year. And in July 2013, ClinGen grants were funded, which represented our U41 grant and the Stanford Baylor and UNC Geisinger ACMG grants. And those 3 grants came together to form what is now ClinGen. And we partnered very closely with NCBI on informing the ClinVar database. So now we had funding. NCBI had launched the ClinVar database. Now we needed more data. And in fact, we had chose to fund a few different laboratories in part to help pilot submission of data. We weren't all storing the same fields on variants and structuring our data in the same way, and we needed to really work closely to develop what we were going to be sharing into this database and how data needed to be structured. So we worked together. There are other early adopters also anxious to share their data, and really began working closely with NCBI. I will point out that although we did fund some of the labs early on as we were piloting approaches, today there are no labs funded by NIH or any other entity to support submission. That is all done voluntarily and supported by the community that submits data to ClinVar. I think also conceptually we're really trying to support why it's important to share data. And I remember a quote that I added here from David Margulies, who's the then director of Corelligen, who said, airlines don't compete on safety. You don't hear JetBlue saying, we crash less than American Airlines. No, you just expect that every person flying has a right to safety. And I think the same is true in clinical labs. Patients have a right for their variants to be interpreted as accurately as possible. And so we really need to think about ClinVar as a pre-competitive space for knowledge sharing, and the laboratories can still compete on services as they do today. And that was an important sort of conceptual grounding in the work we were doing. It was also critical that we established that patient consent was not needed for knowledge sharing. We put out a paper, and in fact the UK group, also dealing with the GDPR, put out a subsequent publication to really define knowledge sharing for variant classification as not requiring patient consent. We did, on the right side of this slide, define what additional data could be shared, individual level data, detailed phenotypes if you had consent, but the actual act of sharing a classification and the aggregate evidence supporting it did not require patient consent, which was critical. We also started thinking about more carrots and sticks for incentivizing knowledge sharing. We provided buttons and stickers that say, I'm a ClinVar submitter, and we made signs that labs could put in their exhibit booths to say, I submit to ClinVar, and really talking up the importance of this and the honor of this, of contributing to the knowledge base. We also then, from a stick approach, launched the ClinGen Lab List in 2017, where we really defined, and on the right side of the slide is the current list that's on the ClinGen website of those laboratories that meet the minimum requirements for data sharing to support quality assurance. And labs every year have to reapply for this and document their data sharing approaches. And this then provides a list for insurers to choose which labs to reimburse and providers to choose which labs to order from if they wish to support the knowledge sharing that's so critical to our field. And I will say, the moment we launched this list, there were a number of laboratories that hadn't been sharing up until that point that really said, okay, it's time, and sort of got on board. So what's the status of ClinVar today? Well, there's now almost 2 million submissions from on over 1.2 million variants from over 2,000 submitters from 80 countries. I have listed the top 20 submitters to recognize just the extraordinary amount of data that's been shared to date. And in fact, 89% of the data in ClinVar is from clinical labs. That was our primary intent. This is some of the best curated data out there, and it's important that we all share and build upon it. There's another about 10% that comes from research studies, mostly in the course of publication. A lot of journals are now requiring submission to databases like ClinVar as part of their publication policies. And then a small fraction coming from expert-curated variants, patient registries, clinics. I have highlighted the labs on the right that are commercial laboratories. So this is not an academic data sharing exercise, as you can see from all of the green. These are commercial labs voluntarily sharing their data because they believe it is the important and right thing to do to build the knowledge base and ensure the most accurate information to patients. Now, we've made a lot of progress in the US, but I've plotted on this graph that by country submissions. So you'll see there's a big disparity between what is being shared in the US versus other countries. And that's in part because we've focused so much energy in the US in getting all this data shared. It just doesn't happen easily. You really have to garner the community and help support the process. And there's over 760 million variants in the Nomad database right now, and there's only about 1.2 million variants interpreted in ClinVar. So we still have a long way to go, and some of this will be working across the globe to incentivize, encourage, and support data sharing from other countries. And we are working on doing that in part through the Global Alliance for Genomics and Health, working with other countries that are in fact working to do this sharing as well, some that already have. I will also say that even once we submit to ClinVar, there's still a large fraction of those 1.2 million variants that are uncertain significance. You can see the yellow pie fraction here that is about 40% of the content is either uncertain or conflicting. The ClinGen expert panels particularly focus on that conflicting set of variants where we can resolve differences in interpretation. We also focus on VUSs that have been submitted by multiple laboratories, figuring that if we aggregate that data together, we can potentially move that variant to benign or pathogenic, and that's happened in many cases. So this is where knowing who's got data on which variants is incredibly helpful to resolve these VUSs. The other challenge, of course, all of you who participate in curating knowledge for variation, it's a labor-intensive exercise. We all read papers, extract information, look at pedigrees, read long text entries in ClinVar and the supporting evidence to bring data together. It's not a easily scalable exercise the way it operates today, and we've got to make it more scalable. So I think to do that, we're going to need access to interoperable primary data sources at scale. And so what do I mean by that? Well, databases that gather population data, like our NOMAD database. We have over 180,000 exomes and genomes. We need much more data than that. And we are working on a release this year of over 700,000 exomes and genomes. And then we'll follow that with V5, where we'll have over 1 million. That's great, but there's still more diversity we need from the global population. We also need more access to high-throughput functional evidence. There's now starting to be assays run that are scanning mutagenesis and other things where we can actually disrupt variation even before we've seen it in a patient, so that the moment we see it in a patient, we can look in a database and say, what effect will it have? But we need to capture that data in structured ways and scalable ways so that we can apply it to our annotation pipelines and understand the effect of variation on function. And most critically is actually access to population data that is phenotyped individuals. And you've heard some talks at the meeting about the use of electronic health records and the phenotypes associated with them, particularly yesterday. So databases like the UK Biobank, the All of Us research program. Just last week, we released the data from 90,000 whole genome sequences associated with individuals recruited through the All of Us research program. This is well-phenotyped data, associated genotype. These are data sets we need. The GBMI program has cohorts around the world with genotypes and phenotypes that have been shared for aggregate analyses. These have been mostly based on array-based studies on the GBMI, but more data is now generated as sequencing data. And in fact, the International 100K Cohorts Consortium is cataloging cohorts over 100,000 individuals from around the world. These databases are going to be critical. They're phenotyped and building genotypes alongside them. Up in the top right are some of the rare disease databases. Sometimes in the biobanks you don't get sufficient representation of rare disease individuals, but there are some deliberate efforts, Decipher, Geno2MP, Variant Matcher. A lot of the rare disease consortia in the US have data in Anvil. These will be critical for really detailed phenotyping for particular rare diseases to build our understanding of those phenotypes. But accessing this data around the world is going to take work and technical skill. And many of these countries don't allow their data to exit the country. You can't just send it to a centralized database. That works great for databases like ClinVar, where there's no privacy or security issues. We can just put it all on the internet. However, when we think about sharing individual level data, we have to think about different approaches. And the concept that we are really working on is called federation. This is where the data sits in their own databases, but we can query those databases and then bring aggregate information together to the individual querying and get permission and manage access to databases all around the world. This works great if there's standardization to the data in those databases. We understand the data models. If we have defined the approaches to accessing and allowing authentication of those researchers and even clinical labs that are trying to get access. There's a lot of infrastructure and approach that needs to be developed to support federated access to data. And we've written some recent papers about those approaches through work of the Global Alliance for Genomics and Health. And one, I think, great example of the notion of a federated database is, in fact, the Matchmaker exchange. And we launched this platform back in 2015, and the idea was to support novel gene discovery. And so in this case, a group of researchers from around the world that had their own rare disease databases agreed to connect those databases through a common API, or application programming interface. We defined a set of fields of the submitter, the name of the gene, the disease or phenotype of the individual, and some optional fields. And really, it's like playing Go Fish. You just send out an electronic message through one of the nodes. It says, I have a patient with this gene as a candidate gene and this phenotype. Anybody have a match? And immediately we'll get matches and electronic communication back. Yes, you've matched with Decipher, and here's the investigator, and an email is sent to both groups connecting them to then correspond on further detailed phenotypes to decide if it's a valid match. This platform has been in operation now for 7 years and has led to the discovery of over 500 novel gene disease discoveries. And in fact, we have a special issue of Human Mutation that's coming out in June that includes 3 papers from clinical labs that are heavily using this platform for clinical genomic testing as they identify novel candidates in routine genetic diagnosis. So a really critical platform both for research and for clinical. But the key thing here is it's based on a federated approach that allows data sharing across the entire globe. And data does not need to move out of the countries where it sits and allows us to get real-time access to these data sets. It is approaches like this that are going to be critical for the future, and we are now starting to pilot a variant-level matching concept to be able to say, I found this variant in a patient, tell me the phenotype of anybody in the world that has that particular variant, and that will be critical, you can imagine, to us interpreting the variation we find in our patients. And with that, I'll just end with my take-home message. And if I haven't convinced you now, to tell you that realizing the promise of genomic medicine for every individual will require collaboration and data sharing at an unprecedented level, and we must all take part. And with that, I'll just acknowledge some of the early ClinVar pioneers. This has been just an instrumental database for our field. And so I want to acknowledge those who've contributed, as well as the current ClinVar team. Also, the early data sharing pioneers who've been part of the ClinGen effort. And ClinGen, of course, is very large. We have 7 PIs and over 1,840 investigators across 45 countries. And then I didn't really get a chance to talk about the work of ClinGen and expert curation, but that's a critical next stage as we aggregate data. And of course, NIH's funding for this effort and the Global Alliance. And with that, I will stop there. I don't think we'll have questions, but you can submit things online, and I'd be happy to answer any questions that come in. Thank you very much.
Good morning. Good morning. Thank you for inviting me. I'm going to talk a little bit about Mendel this morning. Let me grab the clicker. We're approaching Mendel's 200th birthday in July. I have no relevant disclosures, although I should say it's quite likely that at least one of my 4 grandsons thinks I'm old enough to have worked as a paid assistant in Mendel's garden. So, but I didn't. Okay. So speaking of old, some of you may recognize this beautiful structure. Some of you may even have been there. This is Darwin House in the Kent countryside, not too far from London. And this is where Charles Darwin lived for 40 years with his beloved wife, Emma, and their 10 children, not all of whom, I'm sorry to say, made it to adulthood. And this is where Darwin wrote The Origin, The Descent of Man, and many other extraordinary important pieces of work that still influence our work today. Now, this is the classic Sandwalk behind Darwin's house. It's about a quarter mile out. I think he purchased this from a neighbor. But Darwin used to traverse this Sandwalk and ponder questions that were central to his various investigations and his various products. And I traversed this myself a number of years ago during a late winter visit, and I'll have to confess that my only conclusion was that it was really cold, which is just one indication of the intellectual distance between the great man and me. So these are 2 of the questions that Darwin likely pondered while he was wandering the Sandwalk. And you're familiar with these issues, of course. And the questions began to emerge from Mendel's work in this legendary garden, which is now in the Czech Republic. Mendel developed the principles, first of all, he developed the notion of particulate inheritance, and he also developed the principles of segregation and independent assortment, three absolutely fundamental content areas for biology education at all levels. It's very likely that Mendel also read the German translation of The Origin, and so realized that Darwin was struggling a little bit with inheritance. Darwin just could not get it right. Smart as he was, he just did not figure it out. Mendel attended the expansive 1862 international exhibition in London with a delegation from his city of Brno, but there's no indication that he met the world's most famous naturalist while he was in England. And there is still some disagreement among historians of science about whether Darwin actually read Mendel's work. And I'm not an historian of science, but you can take a look at that literature. It's extremely interesting. There's also some question about, given the extraordinary mathematical content of Mendel's paper, which was unusual for that time, there's some question about whether Darwin would have been put off by it, and if he had read the paper, whether he would have understood it well enough to figure out that Mendel actually had the answers to the questions that were plaguing him. So this is, for you guys, of course, nothing but review, but this is some of what I hope we teach about genetics. It is the study of inherited biological variation, and it's the rule in the living world, not the exception. We should be telling all of our students that. We should also be telling them about the extraordinary contributions that Mendel made to our understanding of life on Earth. And you know much better than I, because I'm not a clinician, you know much better than I the extraordinary contributions that Mendel made to genetic medicine. Now, one of the other important pieces of Mendel's work is the demonstration of the mechanisms for biological continuity. So variation and continuity are two of the fundamental supporting structures of evolution theory. And we're cognizant as a society, even if we don't give it much credit, we're cognizant of variation. I mean, look around the room. Look at any classroom you've been in, and you see that variation is evident everywhere. We're also cognizant of continuity. Again, although we don't really talk about it a lot, don't acknowledge it. But again, so here's one illustration. Anybody know where this quote came from? The child is father of the man? Okay, I won't take too much time. This is from the great Romantic Age British poet, William Wordsworth. Here's another indication of our familiarity with continuity. In another time's forgotten space, your eyes looked from your mother's face. I really love that quote. Does anybody know where that's from? Okay. The distinguished scholar Captain Trips from the Grateful Dead, from Franklin's Tower. I love that song. Okay. So, the work of the venerable priest has created a bit of a box for us, in that there's a concern that the focus on Mendelian characters does not fully represent the way inheritance works in any population, but in humans in particular. And there's a concern that the continued focus on Mendelian characters, which largely, particularly at the high school level where I had most experience developing materials, particularly at that level, they're a little deterministic, and they do not acknowledge the notion of continuous variation and the contribution of multiple genes and multiple environmental variables to common complex human characters. And this is a paper by Mike Doherty, whom many of you know, from the American Journal about, 2009. And Mike proposed that we actually should begin genetics instruction with a focus on quantitative characters and not Mendelizing traits. Now, I'm going to spend a little time on this issue because I think it's extremely important. there is an increased concern that the deterministic approach to genetics that's represented in Mendelian characters and our focus on them provides an opportunity to support notions embedded in white supremacy. And so we see this suggestion from BSCS, where I worked, as you heard Dr. Williams say, I worked at BSCS for 22 years and was the director there for 14. They're proposing that we need to focus on genetics education as a way to combat white supremacy. I'm going to talk about this a bit more. Let me see. So I just wanted to share two different perspectives. They're similar, but they come from two categories of scholars. This is a book by a very distinguished historian at Stanford, George Frederickson. And you see what he has to say about the ways in which determinism and typological thinking and essentialism actually help to support notions of racism. Now, here are related contexts from two biologists. The first is from Ernst Mayr, who arguably was the greatest evolutionary biologist of the last century. And if you haven't read his book, The Growth of Biological Thought, I encourage you to do so. It's a humbling experience. And then the second, which actually credits Ernst Mayr, is from our late colleague Barton Childs. But you see the focus here is on the dangers of typological thinking and the ways in which they can feed into these notions of racial superiority or racial types. So the outstanding question is it a good idea to use genetics as a way to combat white supremacy, to say this is an objective of genetics education? I don't think so. So let me explain. I think it's unnecessarily restricted and too focused. I also think it's unnecessarily incendiary. Now, with respect to the incendiary piece, let me assure you that I'm not a stranger to nor averse to controversy in the science classroom. Because of the books I've helped to write and my own teaching, I've been attacked by creationists, by radical animal rights groups, by right-to-life groups. So I've sort of had my existence on the planet threatened and any potential afterlife threatened as well. So I'm not averse to controversy, but I think we have to be careful that what we're proposing has substantive roots in the science we work in. And I think the better approach is to broaden this a bit and make sure that students understand the history and nature and extent of the biological variation that is present in the human population. And we probably, or I hope, will end up at the same place as we would if we said, all right, we're going to take on white supremacy and attack it as a particular issue. I think we end up in the same place by giving students the tools to look at information that proposes that something like white supremacy has any validity at all, and leave them to make the decision or come to the conclusion that it simply doesn't hold water. And what I would like to see is us to get to the point where we're focusing on messages like these. These are from Girl Scout cookie boxes. I've been using these as instructional tools since the early 1980s when they first came out. And I frankly admit that I ate 3 boxes of mint cookies before I realized I had this wonderful instructional tool before me. But you see on one side of the box, it says, I'm not like anyone else. And on the other, it says, we have a lot in common. Now, that's sort of what we do. I think it's a wonderful encapsulation of what we would like kids to know about genetics. So, let me wrap up first by pointing out from this article from Science that geneticists are curbing the use of race. And I've chosen the Science reference rather than the reference from the American Journal of Human Genetics to point out that this information is making it to a broader array of scientists because it appears in Science, right? Okay. So, we have the open question of whether science and whether science education has a political moment, has a political purpose. And this is a quote from a wonderful new biography of J.B.S. Haldane. And I really like this because, again, this is us. This is sort of what we do. We study how people differ from each other. And as Subramanian, the author, says, that is instantly political. So we're not getting away from it. The question is, how do we deal with it? And I hope I've given you something to think about. Thank you.
Terrific. Well, I too am glad to be here. I have to say that I too am going to say a number of things that are really challenging. So let's get going. The question that I want to talk about is, what does the future of prenatal diagnosis hold? I have no financial disclosures.
Oh, right.
Well, if the clicker would work, that would help. Oh, whoops. Uh-oh. Well, okay. What I was going to say is that until recently, the pregnant uterus was a black box. And we didn't know anything about children until they were born. In fact, it used to be that 10 fingers, 10 toes was all that used to matter. A phrase that I suspect many of you will recognize from Gattaca. No more. Starting in the 1970s, it became impossible. It became possible to identify characteristics of the fetus, first beginning with very fuzzy ultrasound pictures, not inaccurate, but tests that weren't very good, like maternal serum alpha-fetoprotein, and amniocentesis beginning in the second trimester, which was invasive, carried with it a risk of miscarriage, and then often took at least days to weeks to get the results back. Boy, has that changed. The biggest change, the one to talk about, is that of imaging. Now we truly can see the fetus. We can see 3D images that are just stunningly clear. These are now marketed to parents as baby's first picture. This is a frame that you can buy from Walmart that you can put your prenatal ultrasound in to show off baby's first picture. But in addition, our technology has changed. First with the development of chorionic villus sampling, which could occur earlier during pregnancy, and now non-invasive prenatal testing, often characterized as, quote, just a blood test, for which we can now not only look for aneuploidies of various kinds, to even in some cases, single gene disorders. So what does the public hear about prenatal diagnosis? They see ads on the web from big companies like Natera and Invitae, which in fact says a simple, safe test. Wow. Well, I edited my slides this morning and they didn't upload. Oh well, that's all right. But what we also know is that these tests are sometimes mischaracterized in the literature. There was an article that came out in Genome Web saying that that prenatal ultrasound can detect autism. Now, there is a study that suggests that some of the things you see on prenatal ultrasound are associated with autism, but you certainly can't make a diagnosis with that. There was an article on New Year's Day in the New York Times highly critical of non-invasive prenatal testing for rare monogenic disorders that led to a lot of controversy. But the fact of the matter is, there's a lot of information out there, and that this is important and people know a lot about this. The good news about prenatal diagnosis, and this is really good news, is most of the time you get good news, that the tests are reassuring. And so this is really good for parents. They like that. But there are some people who don't get prenatal diagnosis. Some women choose not to get it. Why do they choose not to get it? Because oftentimes because they don't want the information, they're not going to change what they do, so they choose not to get it. Other women don't have insurance coverage. This is an area in which the college is working, but the fact of the matter is that Medicaid in many states doesn't cover it. CHAMP VA, which is for the military, doesn't cover it, and federal funding doesn't cover it. So this is a huge issue about lack of insurance coverage. Black and Latinas, for a long time, have used prenatal diagnosis less frequently. And going back to the 1980s, when Raina Rapp did research, she identified some of the many factors that can feed into this, including the idea that this just wasn't socioculturally appropriate, that maybe women didn't see themselves as empowered to make these decisions. Maybe they just didn't have access. This was in New York at the time, which did provide universal access, but nonetheless, there was less utilization. Rural women don't have access, particularly to some of these high-tech diagnostic techniques, like some of the really amazing imaging things like fetal echocardiography. And then finally, we know that there are a lot of doctors who refuse to provide this testing because they just don't agree with it, they don't offer it, they won't take care of the women who want it, and so they just can't get it. And to this day, we don't know how much of the lack of uptake of prenatal diagnosis is due to money, due to lack of desire, due to sociocultural barriers. These are issues that we have to move forward and figure out. But now let's turn to what happens when women do get prenatal diagnosis. The first thing is that although our diagnostics are really good, you have already heard today that our therapeutics are really delayed or behind. And so in most cases, there's very little that you can do during pregnancy that's going to make a difference. One example of something that's possible is surgery for spina bifida, which actually was pioneered here at Vanderbilt, among other places. But fundamentally, there's often nothing you can do other than perhaps figuring out where you're going to deliver in hopes that that will lead to a better outcome, which is often true. But even when pregnancies are carried to term, prenatal diagnosis is not always benign. And I want to talk about some research that was recently done by a resident here at Vanderbilt with whom I worked, but there's a long-standing history that women who get prenatal diagnosis that they have a child with severe congenital heart disease actually do worse over the long run than the ones who discover it at birth. And so this resident interviewed numerous women who got fetal diagnoses of congenital heart disease. And what they found, and what she found, was that particularly the women who found out that the fetus had really severe congenital heart disease were just devastated, and that they had a hard time dealing with the inability to get a definitive diagnosis, even as good as fetal echocardiography is, and by the inability to do anything until the baby was born. The first person that Dr. Harris interviewed when she was thinking about this study was my sister. My sister had a child more than 30 years ago with cyanotic congenital heart disease. And so I said, Dr. Harris, why don't you call my sister and see what she has to say? My sister didn't find this out until the child was born. Happily, the child was born at a tertiary hospital with a fantastic cardiac surgery program. But to this day, my sister says that she is so glad that she didn't know about this before my niece was born. My niece did well, is doing well, gets great care, and has a full and wonderful life. But my sister says, I did not want to know this. The thing that we tell ourselves about preparation and accommodation is not something we should assume, because it doesn't always happen. But the other thing we have to talk about is abortion. And I'm just going to give you a ton of bad news. Just telling you. Pregnant women in many parts of the country either currently do not or soon may not have a choice about whether to terminate a pregnancy or not. The efforts in this country to limit or ban abortion are amazing. Starting at various points in pregnancy. There are a number of states, including Tennessee, that have bills pending that would ban abortion starting at the moment of fertilization. That's going to become relevant to something that I say in a minute. Many states are trying to ban abortion starting at 6 weeks before women know they are pregnant, and for sure before they have prenatal diagnosis. We also have the bounty hunter laws, which we see in Texas and now in Idaho, which say that anybody can sue and get a nice chunk of change from someone who has facilitated an abortion. That will doubtless be brought to include people who provide prenatal diagnosis. And of course, many states, that's what this particular map is, have so-called trigger laws, which say that if Roe versus Wade is overturned, that abortion will be illegal in those states. This is a lot of states, and it affects a lot of women. More particularly and relevant to us are so-called reason bans. Reason bans are ones that say that it is inappropriate to do an abortion on the basis of race or sex or certain kinds of genetic disorders. Sometimes they just mention Down syndrome. Sometimes they go a whole lot further than that. There are 20 states that have these in place. Most of them are enjoined, but I'm going to tell, which means they're not in effect, but I'll tell you more about that in just a minute. But it's important for you to know that in the case of Box versus Planned Parenthood, which is out of Illinois, Justice Thomas went off on what we call dicta, to say that in his view, having an abortion after prenatal diagnosis was modern day eugenics. He said this at some length. That wasn't an issue before the court. So it was just Justice Thomas making comments about it. But based on his comments, the Sixth Circuit, which is Ohio, Kentucky, Tennessee, and a few other states, have some cases that are really of interest. Ohio has a ban has a so-called reason ban. The Sixth Circuit, which is the level just below the Supreme Court, has upheld that. So quote, reason bans are now illegal in Ohio. They are soon going to be illegal in Tennessee because we have an appeal pending. There's an appeal pending before them. Since it's the same judges, it's going to come out the same way. Other circuits do not have struck those down, saying that they violate Roe v. Wade and more particularly Planned Parenthood. But I think, and so we have what's called a circuit split. That's important because the Supreme Court takes cases when there are important circuit splits. And I should tell you that when Box was pending in the Seventh Circuit, which is where Illinois is, that Justice Coney Barrett dissented on thought that the reason ban should be upheld. So that's 2 out of 5. 2 out of 4 already said this. So, but one of the things I want to say, and one of the things that we need to say, you need to say, is the idea that having women have choice leads inexorably to discrimination is just flat wrong. It's just flat wrong. In the 1970s, as prenatal diagnosis was coming into place, there were a number of things going on. Many children with Down syndrome were put in institutions. Their surgical problems were not fixed. Their life expectancy at that time was about 10 years. So very uncommon. Where are we today in 2022? First of all, they get a lot of medical care, including, it's unthinkable not to do the surgery. They get inclusive education. At Vanderbilt, we have a program that's a parallel university program for children with Down syndrome called Next Steps. And if you look at the life expectancy of children, you'll see that instead of being 10 years, it's closer to 50 to 60 years. And this is a result of a number of things. One is that we have enacted laws like the Americans with Disabilities Act, many about more inclusive education, but also important is many women and their partners are choosing not to terminate pregnancies on the basis of prenatal diagnosis. So the idea that this is inexorably going to lead to discrimination is just wrong. And all you have to do, many of you do this, all you have to do is go in a children's hospital and see that the care that is provided to children there is really quite impeccable. So where are we now? The Supreme Court is considering Dobbs versus Jackson Women's Health Organization. As you may know, they've heard oral argument. The actual issue in that case is whether the state of Mississippi can ban abortion after 15 weeks gestation. But the litigants, the parties, both sides, have actually asked the court to decide whether all pre-viability prohibitions are constitutional or not. Now, the court doesn't have to accept that invitation, but nonetheless, it is, it's a very real one. And if Roe is limited, then I think that it would not be a mistake to think that the reason bans are going to come next, given what I've already told you. So what is this going to mean? It's going to mean that women in restrictive states are going to have to travel. It's going to mean that there's going to be more interest in IVF and pre-implantation genetic diagnosis. But remember, if abortion becomes illegal after fertilization, that will be illegal in those states. And so all of this means that there will be even more disparities between between the rich and the poor than there are now, which is really hard to imagine. So what do I think this is going to mean for you? First of all, I think that when making decisions about prenatal diagnosis, women really need to be counseled about what the issues are. Now, I have to say, I worry about that. When I was pregnant with my first child, I was 32. My OB told me that he was really eager for me to get prenatal diagnosis, and in fact told me that if I were his wife, I would have it. But I didn't, and that was partly because I was a lawyer, but I think. But the fact of the matter is, I think many women are going to choose not to get prenatal diagnosis. Because what are they going to do? Just fret. And so this is going to really upend obstetric practice, which I think is going to make the obstetricians fairly nervous. But what it means for you is that you need to be prepared to provide even more support to women and their families following prenatal diagnosis, given that the only option they have is just waiting. Is just waiting. Now, here are my acknowledgments. I wrote my first article about the Yale Law Journal is what I wrote when I was a law student. It was my first article arguing that women have a right to prenatal diagnosis, 1978. I got drawn back in by very people you have to be of my age to know these people, Marjorie Shaw, Elizabeth Thompson, and Karen Rothenberg, and an absolute host of geneticists and genetic counselors and colleagues and students over the years. So you all need to know this is coming. You are going to learn a lot about NIPT and other methodologies like that, and you just need to know what's really going to happen. Thank you very much. you.